Swayam Prabha. Digital India. Educated India.
Hello and welcome to this first class on special relativity. My name is Vikram Ranthala and I'm a theoretical physicist in the Department of Physics at IIT Bombay. At the beginning of the 20th century, there were two big discoveries that completely upended our view of physics as had been given to us by Newton. These two main discoveries were the theory of special relativity and the theory of quantum mechanics. These two ideas have completely transformed our understanding of the universe, our understanding of what physical reality is, and even the basic concepts of space and time. So let's begin by first discussing what we mean by special relativity. Relativity very simply means it's the relative relationship between how different observers view the world. And special implies that you're talking about a special class of observers, and these are observers who are in a state of uniform motion relative to each other. That is, they're moving at constant velocity with respect to each other. And these observers are what we call inertial observers. We'll discuss these ideas in more detail as we go along. So today we're going to discuss three things. We will discuss dictionaries for physical observers. That is, how different observers translate ideas of physics between themselves. In particular, we'll talk about the ideas of Galilean relativity that all of you are probably used to. And we will discuss how different observers in a state of uniform motion relative to each other translate different observations. We'll then see that physical laws, like Newton's laws, actually obey this principle of Galilean relativity, and that is why it seems so intuitive to us. So let's begin by discussing the ideas of dictionaries for physical observers. We'll start by first talking about how a particular physical observer makes observations. So in order to talk about things in the world around us, we first start by, let's say, talking about particles. Okay, so suppose we have a collection of particles of different types, perhaps, and we want to describe simple things like what are their positions, what are the speeds at which they're moving. And then we can talk about more complicated things once we can describe their positions and their speeds. And we need to describe their positions and speeds at different instants of time. So in order to establish their positions and speeds, we first need to establish a coordinate system. So how do we establish a coordinate system? Well, we start by defining an origin. So we define an origin. And then we define several coordinate axes. So since we live in three spatial dimensions, we define an x direction, we define an orthogonal y direction, and a third orthogonal z direction. And now that we have a set of axes, we can talk about the positions of different particles. And the way we do this is we simply drop perpendiculars from the particle's position onto different planes. So for example, if I want to know the z coordinate of this particle over here, I would simply look at the perpendicular dropped from this particle to the xy plane, and this length over here would give me the z coordinate. Now, in order to describe the length, I need to have a standard reference length with which I choose to describe it. So what I need to do is then assign some distance on the x-axis as a distance of 1 meter. Let's say I place a meter stick along this, and now I have a fixed reference length. Okay, so now if I want to describe the z coordinate of this particle, what I would do is see how many meter sticks I need to place together and take the readings on this meter stick at this position. And so I would say perhaps that this is 1 meter stick, 2 meter sticks, and maybe half a meter stick more. So the z coordinate of this particle is 2.5 meters. So similarly, I can get an x coordinate and a y coordinate. For the x coordinate, I would drop a perpendicular onto the yz plane, measure how many meter sticks across I have to go to get this coordinate, to get to this point. Okay, and I would say that that is the x coordinate. And similarly for the y coordinate. So at the end of this, I would have 3 coordinates to describe this particle. I would have an x coordinate, a y coordinate, and a z coordinate. So let's recap the essential things that we needed to describe the coordinates of this particle. We need an origin of coordinates. We need a set of reference axes, and we also need a standard ruler or meter stick with respect to which we can measure distances. Okay. Now, we can use this to describe the coordinates of any single particle or set of particles. So if we have a collection of particles, we would have the positions for each particle. So there would be triplets, x1, y1, z1, describing the coordinates of one particle, another set describing the coordinates of a second particle, and so on. Okay, and you could describe all their positions. However, the world is interesting because of dynamics, because these coordinates change with time. And that is how we can describe things like velocities and accelerations and forces and collisions between particles, is only if we can take into account the dynamics, how these positions evolve with time. So if we describe every particle's position by a vector, so let's call this the vector x1 bar, okay, which denotes the position, the vector position of the particle, which has, in our coordinate system, has these 3 coordinates. And this is the position of particle x2, which is x2 bar. And this is the coordinate of the particle at a particular time, t. And now we can describe the coordinates of every particle at every instant of time. So this vector x1 bar is a function of time. The vector x2 bar is a function of time, and so on. Okay. There is no physics in this. This is just a description of the world. Okay, or of the coordinates of the world. Okay, so it's an assignment of coordinates. By the way, one implicit thing here is that we also need to pick an origin in time with respect to which we measure time intervals. So we want to choose a 0 instant. That is, what is our reference time? So we start all our clocks at a time 0. And we wait. So our clocks, let's say, start at 12 noon. And then we wait some amount of time, and let's say some amount of time has passed, and the clock now shows 12:15. Okay, so this is our t is equal to 0 moment, and this is t is 15 minutes later. Okay, so this defines our origin in time. Okay, we chose a particular reference point. This reference point could have been arbitrary. Of course, we could have chosen 1 p.m. or 1 p.m. And 13 seconds as our reference time. That choice is completely arbitrary. Okay, just as when we chose our spatial coordinates, the choice of origin of coordinates was arbitrary. The choice of set of reference axis was arbitrary. And the standard ruler or meter stick was also arbitrary. Okay, we are measuring things relative to some fixed length. Okay, but what that size of that fixed length is could vary. We could have chosen a 2-meter stick as our reference length. Okay. Similarly, we have two things that we can choose here. We can choose an origin in time, which is again an arbitrary quantity. And we could also choose an interval of time, just like we chose a standard reference length, we choose a standard reference time. Okay, how do we choose our reference times? Well, we choose them based on a natural clock around us. For example, we take the motion of the Earth around the sun, and we subdivide, and that defines a 1 year for us. Okay, and then we define things with respect to intervals of 1 year. So, for example, a day is 101 by 365 of a year. An hour is 1 by 24 of a day, and a second is, an hour is 1 by 24 of a day, and a minute is 1 by 60th of an hour, and a second is 1 by 60th of a minute. Okay, so the interval of time, of course, choosing even a year is an arbitrary reference. Okay, we could have chosen any interval of time as our reference, and so we can measure time with respect to seconds, days, years, months, or we could have measured, our reference time could have been 3 seconds, and we could have measured things relative to how many 3-second time intervals have passed. So the origin in time and the interval of time are arbitrary, and again, this is a choice of coordinates that we're assigning to time to describe the time location of a particular particle's position, let's say. Okay, so once we have set up these coordinate systems, we can now describe dynamics. Okay, so we are now ready to describe dynamics. And the dynamics have to do with, if I take the positions of particles at some instant of time, so I have a collection of particles, where these are different functions of time, but I don't know what these functions of time are. I just know that I can assign a position and a time, okay, to where the particle is. So I can assign a position to where the particle is at a particular instant of time. But what I really want to know is, how does the position of a particle change with time? Or how does the position of any particle in my list change with time? Once we ask these kind of questions, we are talking about dynamics. Now, besides wanting to describe the positions of particles as a function of time, in physics we're interested in other kinds of things like waves. So in order to describe waves of different kinds, for example, waves traveling or ripples traveling on the surface of the ocean, or waves set up on a string, for example, of a guitar, or if we're talking about things like light waves, which are electromagnetic waves, we might want to be able to describe these things in some way. And the way we do that is, let's take a particular example. Let's take the case of electric fields. Let's take electric fields. So the electric field is described by a vector, E, where at each point in space I assign a vector. Okay, and this vector is the vector of the electric field. So the direction of this electric field tells me which direction the electric field is pointing at that particular position in space. And its magnitude tells me the amount of electric field, that is how strongly charges will feel the influence of this particular electric field. So the thing to remember is that this length has nothing to do with length in physical space, that is, it's not a length between two positions in space, but rather it's the magnitude or the strength of the electric field, which I'm just representing in a drawing over here by showing a length in space. Okay. Now you imagine that at every point in space I have an electric field, so there is a vector that describes the amount, the direction, as well as the magnitude of the electric field at each point in space. So this is at the point 1, this is at the point 2, this is the electric field 2, this is at point 3, there's electric field 3. And these could have differing lengths. Which means that they have different magnitudes at each position, and they have different directions at each position. So how do we describe an electric field? Well, again, we still need to set up our spatial locations because we need to describe what the electric field is at a particular location in space. And the other thing is, these electric fields could be changing as a function of time. They could be responding to the motion of charges. Okay, so if I have a charge, so we know that if you have a single point charge, this can create an electric field around it if it's at rest. And if it's in motion, it can also create magnetic fields. So if this charge moves, the electric fields move along with it, and it also creates magnetic fields. So we need to be able to describe the electric fields everywhere in space and at all instants in time. So in other words, we need to be able to talk about things like what is the electric field at a spatial position x at a time t. Okay, so once again, we need to be able to define a spatial coordinate, and we need to be able to define a time coordinate, which again requires that we define an origin, a set of axes, and a reference length to measure positions. And to measure time, we need to define an origin and a reference time interval. To measure electric fields, we would also need a reference electric field. Okay, and we're assuming that the coordinate directions with which we describe the electric field will be the same as the coordinate directions with which we measure our positions. All right, so whether we're describing the positions of particles as a function of time, or whether we're describing electric fields or ripples of a water wave, we need to be able to set up some way to describe positions and times. Okay. So now in this way of looking at the universe, we need to describe positions and times. So for particles, we need to describe how their positions are changing as a function of time. For fields, we need to describe how, for example, the electric field is changing as a function of different spatial coordinates and different times. Okay, so this kind of field is called a vector field. Okay, and you need three numbers to describe the electric field at every position. You need to be able to describe the x component of the electric field, the y component, and the z component. But you can also have what are called scalar fields, that is, fields like the electric potential, which is a single number at each point in space and time. So this is called a scalar field. And if we want to describe all kinds of interesting dynamical processes involving particles and fields, we need some kind of dynamical equations. And these dynamical equations tell us how quantities like x of t change with time. That is, how does this function x of the position of a particle change with time? And how does the electric field change as a function of both spatial position and time? Okay. Now, just to be clear about the distinction, the electric field is described at all positions and at a particular instant of time. This position here describes specifically the position vector of a particular particle. So this vector x is not the same as this vector x. This is a general position of a particle. So we could have just as well denoted it with some other symbol. We could have used the symbol y to denote the position of the particle. Okay, so this symbol here refers to the position of a particular particle that we're talking about. So let's say particle 1. Okay, whereas this coordinate describes all positions in space. So for every position x, I need to be able to write down what the electric field is at every possible time, all possible times. Okay, and for a particle, I need to be able to specify where it is at all possible times. Okay, so what we need are dynamical equations which tell us how quantities like x or y change as a function of time. The position of particle, how does it change as a function of time? And how does the electric field change as a function of both space and time? So for particles, they obey Newton's laws. And Newton's laws tell us that if there's a force acting on the particle, this force will produce an acceleration. So this is Newton's second law. Force is mass times acceleration. And the acceleration is the second derivative, or the rate of change of the particle's position as a function of time. Where this derivative is taken at some instant of time t. Okay, so what this does is it tells us how the second derivative of x of t, that is how this vector x of t, it describes the rate of change of this vector. Okay, and the rate of change depends on the forces applied to a particular particle. So given an initial position, so supposing we know the position of the particle at some time t naught, and suppose we know the velocity, that is the rate of change of position at some time t naught, and suppose we know the forces acting on the particle, that is we know how this force and how it acts on the particle, we can solve this equation. It's a second order differential equation. We can solve this equation to figure out how the particle moves as a function of time. So given some initial conditions, and given the forces acting on the particle, you can figure out the trajectory. That is what the particle will do in the future, okay, under the action of those forces. So this is what we mean by dynamics. We can figure out the motion of particles under the influence of its interactions with its environment. Similarly, for electromagnetic fields, we have Maxwell's equations that tell us their dynamics. So I'll just write down Maxwell's equations. So the first one is about the divergence of the electric field is related to the charge density at a particular location. So this is the divergence of the electric field at a particular location x and t, and this is the charge density at that location x and at the same time t. So the second equation tells us that the curl of the electric field is related to minus the rate of change of the magnetic field with time. Okay, this is called Lenz's law. So this is Coulomb's law. The divergence of the magnetic field at any location is zero. This is simply because, in analogy with the electric field equation, charges source electric fields, but there are no, as far as we know, there are no magnetic monopoles in nature. So this is telling us that there are no magnetic monopoles. And lastly, the curl of the magnetic field is equal to the rate of change of electric field with time multiplied by epsilon naught plus mu naught times J. This is Faraday's law. Okay, so you have four equations. Well, in reality, this is slightly more than four equations because this is a scalar equation. The quantity on the left is a scalar, so this is one equation. This is three equations since it's a vector equation. This is again a scalar equation, so this is one equation. And this is three equations, again, since it's a vector equation. So the total number of equations that we have, Maxwell's equations, is 3, 4, 7, 8. 8 equations. And these equations describe how the electric fields and magnetic fields change at different times. So they describe the dynamics of the electric field. For example, if you don't have any charges or current densities, then you can show that you can combine these Maxwell's equations to get a wave equation. So you can show something like this. Okay, in the absence of charges and current densities, you can get an equation of this form. So this is a wave equation. And of course, we know that light is a traveling electromagnetic wave. Okay,